So first of all, we had sequences. So, I mean, the first thing to get comfortable with sequences is to understand the notation, and chiefly what can be done with subscripts and so on. And so typically we denote a sequence with a letter X, say, and we use subscripts to indicate the position of the term in the sequence. Okay, so a sequence would typically go x1, x2, x3, so on. Those would be the elements of the sequences. And this compact notation up the top, curly brackets xn, n equals 1 to infinity, that denotes the whole sequence as one kind of contained object. Okay. Don't get confused with those curly brackets, the way they're used in sets. Okay, a sequence isn't exactly the same as a set. A set is a collection of unordered elements. Okay, but a sequence, even though we're using those same curly brackets, but we're using them in a different way, a sequence is an ordered set of elements. There is one which is the first one, there is another one which is the second one, another one which is the third one, and so on. So they come in a definite order. Okay. Oftentimes we have our sequences defined by a nice formula, a formula in terms of the indexing subscript, xn, given by some formula. And you should also be able to, you should be fairly confident in handling variations on the index position. So if that sequence there is defined by xn, it's 2n over n squared, then what would be the, how would you describe the element of the sequence at position k plus 2? So this is x subscript k plus 2. So you should be, know how to correctly substitute variations of the index position into the formula. Okay. And we had some other terminology then, which was about monotonic sequences or increasing and decreasing sequences. Okay, so sometimes, some sequences have this nice behavior that they're always increasing in value. Some sequences have this nice behavior that they're always decreasing in value. Okay, so that can be captured in a couple of different ways. One way is to look at the difference between consecutive terms. So if it's the case that an minus an plus 1 is always positive or negative, then that corresponds to decreasing or increasing behavior. Yeah. But just to note that you can also capture that by talking about the ratio of consecutive terms. You don't have to use the difference of consecutive terms. You can talk about the ratio of consecutive terms. As long as you're sure that none of these terms are zero, because it never makes sense to put a zero in the denominator of a fraction. So if an divided by an plus 1, if that's always strictly bigger than 1, that means the an is strictly bigger than an plus 1. So that's going to be a decreasing sequence, because each element of the sequence is smaller than the one that came before it. So it's decreasing. And similarly for increasing, the inequality goes the other way. Okay. Now, there's nothing that says you have to consider an over an plus 1. You could consider it the other way around, an plus 1 divided by an, but then you'd have to change the direction of the inequalities accordingly. So don't just try and learn it off by heart, off by rote, because then you might forget, mix up which one goes on top. Just consider it, just remember that you form the ratio of consecutive terms, and whatever way you do it, you compare it to 1. And depending on which way the inequality is, that tells you that the sequence is either increasing or decreasing. Okay. You recover this inequality by cross-multiplying this. You multiply both sides by an plus 1. Get rid of the an plus 1 there and put it over on the right-hand side. Okay. Yeah. Then we have the definition of convergence of sequences. Well, we have the informal definition that a sequence converges to a limit if the elements of it are getting closer and closer to the limiting value. There's nothing incorrect about that definition. It's fine as far as it goes, except it's a bit vague and wishy-washy. You can't build rigorous arguments on top of that definition. Something is converging if it's getting closer and closer to. So there's an awful lot of subtle, sophisticated, different behavior that's just covered by that phrase, getting closer and closer to. Okay? If you want to prove things about the phenomenon of convergence itself, you need something a bit better than just saying it's getting closer and closer to the limit. Even though there's nothing wrong, there's nothing incorrect about that, but it's not detailed enough. It doesn't expose enough of the technicalities of what's going on. So we need a better, more formal, rigorous mathematical definition. And this is it here. Now, when we met it first, we met it in like an English sentence. But of course, now that you've done a bit more logic, you've learned about logical quantifiers and how to construct formal logical sentences. So this would be how we would write down the definition of convergence for a sequence. It says, so we're saying that the sequence AN is convergent to A, if and only if, so this is the formal definition of it here, if for every epsilon greater than 0, there exists some n, capital N bigger than 1, such that if n is bigger than or equal to capital N, then the absolute value of AN minus A is strictly less than epsilon. Now, on the one hand, that's just a kind of a abstract, maybe hard to understand logical sentence with a couple of quantifiers, a universal quantifier for all and an existential quantifier backwards E. But you should also be able to look at that and read it in English and attach the meaning to the different parameters there, okay? This absolute value of AN minus A, this is the distance between the sequence element AN and the claimed limit A, okay? The absolute value of the difference of two numbers. That's the distance along the number line between the two numbers. Okay? And we're saying something about this distance being smaller than something, smaller than this value epsilon. And the sentence is saying for every possible epsilon, strictly positive. Okay, so for every possible distance epsilon, there exists some point capital N, which is a value for the, which is talking about the indexing variable n. There exists some point, and for every little n bigger than that n, this inequality is true. So for any possible distance specification epsilon, there exists some point after which the sequence elements are within that distance of the claimed limit. Okay? And that has to be so. There has to exist this point capital N for any possible positive specification for the distance epsilon. Okay? So you should be able to recognize that formal definition of convergence. But note that it's formal, it's technical, it's very sensitive to, like, if you suddenly swap the position of the epsilon and the n for all in the existence, you're talking about something else. I mean, it's quite a sophisticated logical statement, and it's, you mess around with it, it possibly be talking about some other concept, not necessarily convergence. Any questions about the definition itself just now, or any queries? Anything more I could say about it? Okay. So please interrupt at any time if there's anything that occurs to you that you want to ask. Our main results about, or one of the main results about convergence of sequences that we made a lot of was this algebra of limits theorem. So this was about being able to draw conclusions about the convergence of certain sequences which were made up or assembled out of other sequences. Okay? And knowing the convergence information about the ingredients, how that tells you the convergence statement for the new sequence that you construct out of these other known sequences. So to look at it in detail, we're talking about two known sequences, a sequence AN and BN. They're both convergent, so we're saying the ANs converge to A, the BNs converge to B. And we have three different ways of forming new sequences. We can form a new sequence by taking a fixed linear combination of AN and BN. So the nth term of our new sequence is alpha AN plus beta BN. Alpha and beta are just two fixed coefficients. And the theorem says this new sequence, is convergent, and the limit that it has is the obvious one. Alpha times the limit of the first sequence plus beta times the limit of the second sequence. Okay? So there's nothing funny that goes on. The same transformation you apply to the sequence terms is the same transformation that gets applied to the limit. Okay? And a similar statements talking about products and quotients. If you form a new sequence where the nth term is the product of the nth terms of the two original sequences, that again is convergent, and its limit is the nice obvious choice, the product of the two limits. Okay. And similarly for quotients, except with quotients, we got a few extra caveats, a few extra conditions, which is just about avoiding 0 in the denominator. Okay? So if you've got a sequence, if your sequence Bn converges to 0, you can't apply this quotient form, the algebra limits theorem. Okay? But as long as 0 is avoided by the sequence Bn, that quotient form will go. Okay. Okay. Any questions about that? Okay. So that can be used to determine the limits of compound sequences. Sequences that, when you look at the formula for them or the specification of them, are built up out of simpler sequences. And there was a technical result there called the monotone convergence theorem, which we certainly didn't prove. The proof of this kind of turns on some of the technical details of the specification of the real numbers over the rationals. But what the monotone convergence theorem says is that every bounded monotonic sequence is convergent. So for example, if we prove that a sequence is bounded above, so sequence AN, all of the terms of it are strictly less than some upper bound, capital M, and you also know that the sequence AN is increasing. So the sequence AN is forever getting bigger and bigger and bigger and bigger, but there's a limit to how big it can get. Well, the monotone convergence theorem tells us, well, that forces the sequence to converge to something. Not necessarily to M, the upper bound, could be something smaller than M. M could be like a generous upper bound, you know, the sequence mightn't get anywhere near M. But the monotone convergence theorem tells us that that the sequence has to be convergent. Okay, and we can sometimes use that to draw conclusions about the convergent status of some sequences. There was this device called L'Hopital's rule, which we didn't make a huge amount of. I'm kind of mainly postponing the discussion of that till we're talking about differentiation in detail. But since it is applicable to convergence of sequences, it makes sense to mention it here. So L'Hopital's rule can be applied where your sequence term, AN, is a ratio of terms, Fn divided by Gn, where f and g are a pair of differentiable functions. Nice functions that you can take the derivative of. And this result can be applied in the cases where both the top and bottom are divergent and converging to infinity. So where both the top and bottom are unbounded sequences, or in the case where they're both converging to 0. Okay. Now, the algebra limits theorem is no help to you to determine the limit of AN, because you're either trying to say it's infinity over infinity, which is not defined, or you're trying to say it's 0 over 0, which is not defined either. Okay? So the algebra limits theorem is no help. But L'Hopital's rule says that if there is a limit for this, it will be, or if you can carry it, if this is a valid procedure, if when you differentiate it separately, the top and the bottom of the definition of AN, if these two new sequences, so defined by the derivatives of f and g, if those two new sequences are convergent and it makes sense to apply the quotient rule, then you can. You can say that the limit of the original sequence is equal to the quotient of, not of the limits of f and g, but of the limits of their derivatives. Okay. Now we'll give an argument for why that's true and justify that when we come to study the derivative later on. Okay. Okay. Another type of sequence that we met along the way were sequences that were defined by recurrence relations. So for example, here's a sequence AN defined by a recurrence relation. So this is a situation where we separately give the initial term A1. So A1 is specified to be 3. And then you have this recurrence relation, which is a rule for defining the next element of the sequence, AN plus 1, in terms of the previous one, AN. So since we have a value for A1, the recurrence relation tells you what A2 is, and then the recurrence relation again tells you what A3 is in terms of A2, and then what A4 is in terms of A3, and so on. If we know that the sequence AN is convergent, which we might have been able to prove using the monotone convergence theorem, because by analyzing the recurrence relation, you can sometimes show that it has to be either increasing or decreasing, and that the whole sequence is bounded. So sometimes you can reach a conclusion that the sequence has to be convergent. Well, in that case, you can actually, in effect, solve the recurrence relation to determine what the limit is. If you know there is a limit, then you can simply take the limit of both sides of the recurrence relation. And the limit of the sequence term an plus 1, well, that's going to be the limit a as well. Okay? So if a is the limit of the sequence, then we've got an a on the left-hand side when you take the limit, and on the right-hand side, well, this is a linear combination of an, half times an plus a constant. So its limit by the algebra of limits theorem will just be that same linear combination of the limit of a. So you get an equation in terms of an, which can then be solved to give the value of the limit. Okay. And this particular thing that comes out is just a linear polynomial, so it has a unique solution, which is whatever it is. A is equal to the half of a plus a is 6, isn't it? Is that right? No. 6 is a half of 6 plus 6. Yeah, a is 6. A is 6. If sometimes for more complicated recurrence relations, you might get a higher order polynomial here, a quadratic or a cubic and so on. So it might have a few different solutions. Now, which one is the limit? They can't all be the limit, of course, okay? Because sequences, if they are convergent, they just converge to one thing. So if you get multiple values out of this polynomial, some of them you'll have to discard. And normally you can figure out which ones to discard by knowing something about the bounds on the original sequence. Okay? So if you study the original recurrence relation and you know it's bounded between certain values, then if some of the roots of the polynomial lie outside of those bounds, then you know that they can't be the limits. Okay? Because the sequence can't get anywhere close to those if it's bounded away from those values. Okay, so that was my remarks about sequences. And then we go on to series. Any questions at the moment? Sure. Again, do just interrupt me if you have questions you want to ask. So for series then, okay, we got to understand the basic notation. Again, we're using index variables, but now we're not just observing a list of numbers, an evolving list of numbers. We're now looking at an evolving sum, okay, where we're adding up all the elements from the sequence, so to speak. Okay, so we're talking about y1 plus y2 plus y3 plus and so on. And we're particularly talking about infinite series here. Okay? And we use the capital sigma notation, capital Greek letter sigma, to denote summation, and put subscripts and superscripts on it to denote the start and ending value of the index variable. So this unending infinite series is denoted by sigma m equals 1 to infinity of ym. Don't get too attached to using m's for the indexing variable. You can use anything at all for the indexing variable, but traditional choices tend to be n, m, k, I, j, things like that. They tend to get used, as opposed to using a or b for the indexing variable. They're just some kind of loose conventions around about what's appropriate for an indexing variable. Chief choices will be n, m, k, I, and j, maybe l. So, okay. But in principle, there's you can use anything you want for the indexing variable. So in particular, these two pieces of notation, sigma k equals 1 to infinity of yk, and sigma I equals 1 to infinity of yi, those are denoting exactly the same thing. They're denoting the infinite series y1 plus y2 plus y3. It makes no difference at all that you're using a k here and an I over there. They're both referring to exactly the same thing. Just a different choice of variable for the index. Now, there's a kind of conceptual problem with infinite series, because if you think for your primary school understanding of addition, okay, you can add a finite bunch of things together. You can calculate what its value is. Nothing too strange about that. But an infinite sum, you can never finish physically adding up or computing an infinite sum. The computer could never finish an infinite amount of operations. So what is there any kind of meaning you can attach to that? Well, there is. And we do it using the concepts we already have of convergence of sequences. So we do it via this device called the partial sum. So the partial sum of a series is just when you stop the addition at some point. So Sj is adding up all the yi's from I equals 1, not to infinity, but to this value j. So Sj would be y1 plus y2 all the way up as far as yj, whatever j happens to be. That's called the partial sum. And it's via these that we define the infinite sum. So when you've defined Sj, you can then talk about the sequence of partial sums. Capital S1, capital S2, capital S3, and so on. So this is the sequence of partial sums. Each partial sum is one term larger than the one that came before. Okay. So we've now got a sequence of values, but we already understand convergence of sequences. So if that sequence of partial sums is convergent, if it has a limit, then that is the value we attach to the infinite series. And it makes sense. If your sequence of partial sums, if your growing sum is itself converging to something, settling down to some limiting value, then it makes sense to use that value and attach it to the infinite sum. And say, in the limit, when you add up all of the infinite amount of terms in the series, you actually have that limiting value. Okay, so that's general definitions. To come down to ground a bit and say something concrete, one important class of series that we looked at were the so-called hyperharmonic series. And these are the series where you're adding up the reciprocal of m to the power p. For some fixed value p, you're adding up all the quantities 1 over m to the power p, as m goes from 1 to infinity. And we found that this was a convergent series whenever p was strictly bigger than 1, and divergent whenever p was less than or equal to 1. This was justified using something called the integral test. Okay. And a particular nice importance, one of the very first examples we looked at was when p equals 1, the actual harmonic series, which was a divergent. Remember, the key point about these is, in particular, the harmonic series, which is 1 plus a half plus a third plus a quarter, it's divergent, even though the things you're adding on, the steps you're adding on each time are converging to 0. So the steps are evaporating, so to speak, getting smaller and smaller without any lower bound. So the steps are gradually disappearing, but there's enough weight in them such that when you add them all up, you still have a divergent series. You still have something which is growing without any upper bound. So that's slightly paradoxical when you meet it for the first time. You would think some kind of process where the little increases you're adding to the process are themselves evaporating, converging to 0. You would think that that thing would come to a limit, maybe naively, but it doesn't have to. Okay. So these series where the step sizes are converging to 0, these are the hard ones to judge. So we can't say, it isn't obvious whether they converge or diverge. And that's why we need all these convergence tests. We do, before we meet the convergence test, we do have a somewhat similar result to the algebra of limits theorem for sequences. We have a result about linear combinations of series. So if we know we have two convergent series, a sum of am and a sum of bm, if they're both converging to a and b respectively, capital A and b, then if you form a new series, which is defined as a linear combination of the old series, this new series that you've formed is again convergent, and the limit that it has is the obvious one. Alpha times the sum of the first series plus beta times the sum of the second series. Okay, so we have a big collection of convergence tests for series. The very first one, and this goes back to the remarks I was saying about the harmonic series. The first one is the general term test. And this just makes it very clear, confirms the kind of intuition we have, is that if the terms of your series, if they're not converging to 0, if the step size that you're adding on to each partial sum to get the next partial sum, if those steps are not converging to 0, then the series cannot be convergent. It has to be divergent. Okay? If you think about if these step sizes are not converging to 0, then every so often, the next partial sum is going to change by a significant amount. Okay? It's going to make a significant leap away from the value of the previous partial sum. If it isn't the case that the the series terms are converging to zero. Because if it isn't the case that the series terms are converging to zero, every so often you're going to get a significant series term arising. To look at this result from the other direction, if we know that the series converges, then we definitely know that the series terms are converging to zero. Okay. Now, it's important to recognize that the implication goes in a certain direction. If the series is convergent, we know the terms converge to zero. The implication does not go in the opposite direction. Okay. Just because you know the series terms converge to zero, that does not tell you that the series converges. The counterexample to that, the famous counterexample we have is the harmonic series, where the terms are converging to zero. 1, 1/2, 1/3, and 1/4, they're converging to zero, but that is not convergent. Okay, this is divergent. So that's a counterexample. The fact that this is divergent. Sorry, those over there, I might be able to see. I'm just saying it's the harmonic series, just reminding you that it's divergent. That's a counterexample to thinking that this implication might go the other way. The implication doesn't go. Just go that way. Any questions on that point? Okay. Let me have a whole series of tests, which for certain types of series do give us conclusions about the convergence or the divergence of those series. The nicest one is the geometric series. And it's nice in the sense that it actually also tells you what the value of the infinite series is going to be. I think this is the only one kind of like that. Most of the other convergence tests, they just tell you whether they might be able to tell you whether a given series is convergent or divergent. For the most part, they don't actually supply what the value of the limit is, whereas the geometric series does. So geometric series are ones which match this pattern of that series there in the first line, the sum of a times r to the n minus 1. These are particularly nice series. They have some initial term, which will be a, and then each subsequent term is generated by r times the previous one. So they're series defined by recurrence relations of field. Okay. Each next step size will be r times the previous step size. Okay. And we analyze these and we reach the complete knowledge about them. They convert, well, as long as it's not a trivial thing. If a was 0, then every term would be 0, and it would be very interesting. But if a is non-zero, so if it is a non-trivial series, then it converges if and only if r has absolute values strictly less than 1. In all other cases, it diverges. So if absolute value of r is greater than or equal to 1, then it diverges. And when it converges, we know exactly what the limit is. It's a over 1 minus r. Okay. Now, with all these convergence tests, we have the issue of, when do you use them? Given a particular series, when do you use one test over when do you use another? Well, there's no kind of exact rule for this. It's something of a trial and error process, and you do get a feel for which sequences are better, are more amenable to certain convergence tests. We might recognize when a geometric series, well, we have to recognize the geometric series test can only be applied to the geometric series. So you would have to map your series to that particular form. Okay. The integral test, so this is the one which gave us a rigorous conclusion about the harmonic series and all the associated, the kind of sister series, the hyperharmonic series. And the integral test works by comparing the sum of the infinite series to the behavior of the integral of the function which defines the series terms. So this is applicable in the situation where the series terms am, where those values actually come from a nice continuous function f, which it's possible to integrate. Moreover, the function f has to be decreasing. Well, if the series is to have any chance of converging at all, the function should be decreasing. Converging to 0, effectively. And then, so if the infinite integral of the function, if that exists and is finite, so if the infinite integral is convergent, then the infinite series will be convergent as well. Okay. But again, this test doesn't tell you what the actual limit of the series is. It just tells you whether it's convergent, or it might be able to tell you whether a particular series is convergent or divergent. The comparison tests are important. We had two of them, a standard comparison test and a limit comparison test. The standard comparison test works by establishing an inequality, comparing the series you're examining, which is this one up here, the sum of AM, comparing it to a series where you know the convergence status of it. I've used two series CM and series DM as the comparator series, the ones you're comparing to, comparison series. So the C one is a convergent one and the D one is a divergent one. So this series can give, you can either say your series is going to be convergent, or it might say it's going to be divergent. It depends on what kind of inequality you're able to establish. This only applies to series with positive terms, series where the terms are all positive. But if you can show that your terms are no bigger than the terms of a convergent series, then you also know your series is convergent. Remember, infinite series of positive terms, the reason they converge is because the terms converge to zero fast enough. So if your terms AM are smaller than the convergent ones, that means they're converging to zero even faster. So the partial sums increase less than the partial sums of CM. So they converge better in a way. Similarly, your divergent series, the sum of DM, the reason that diverges is because its terms do not converge to zero fast enough, like the terms of the harmonic series. These are converging to zero, but not fast enough to ensure that the infinite series converges. So if you can show that your terms are even bigger, or are no smaller than those divergent terms, then your terms can't be converging to zero fast enough, because they're bigger than the terms DM, and they aren't converging to zero fast enough. Your ones are even worse than them. They're bigger than. Okay? So then you conclude that your series is divergent. These comparison tests, they tend to be very useful for series where the term is a rational function, meaning a quotient of polynomials in the indexing variable. So if your term AM is some polynomial in M divided by another polynomial in M, then normally this comparison test will be the one to use. This one, or the limit comparison test. And you compare it to the appropriate hyperharmonic series. I think I say on the next slide or the one after it how you figure out which one to use it for. So we have a sister test to that called the limit comparison test. The limit comparison test actually tends to be the easier one to use, I feel. And that's where you're not trying to establish an inequality between AM and CM or AM and DM. Instead, you're forming the ratio AM divided by CM or AM divided by DM and taking its limit. There's a slight difference to the way the conclusion works, but if basically for the convergent case, if you can show that that ratio has a limit, a finite limit, then you'll be able to conclude that your series is convergent. Whereas on the other hand, if you show that the limit of the ratio AM over DM is equal to L, and this L is non-zero and possibly infinite, then you'll know that your series is divergent also. Okay. Now, what's going on in this test is we're showing that eventually your series terms eventually act like the scalar multiple of the comparison series term. And if that's the case, then the sum of your series terms should act like a scalar multiple of the sum of the other series terms. If the other one is convergent, so is yours. If the other one is divergent, so is yours. Now, as I say, the task with these convergence tests, these comparison tests, is working out which series to compare to. So as I said, these are typically used where the series you're looking at is a ratio of polynomials in the indexing variable. And the series you compare it to is the hyperharmonic series, the sum of n to the power d, where d is given as the degree of the numerator polynomial minus the degree of the denominator polynomial. Okay, because the degree of the polynomial is the most dominant power of n that there is in the polynomial. So you've got n squared divided by n4, so you'd be looking at the sum of n to the power minus 2, okay, because d is the difference in the degrees of the numerator and the denominator polynomial. So you'd be comparing that series to the sum of 1 over n squared, and the sum of 1 over n squared is a convergent series. So you'd hopefully be concluding that that series is convergent. Okay, be prepared for some trial and error, some kind of experimentation around. Okay, so I'll probably finish these slides. There's just 1 or 2 slides to come. I'll finish those, and then then we'll have a short comfort break, and then we'll have a look at the mock tests. And I've got handouts of the second mock test to show you. We can go through the mock test questions in the second session. Okay, so there's still another couple of tests to look at. We have the alternating series tests. So this one is appropriate for alternating series. Alternating series are ones where the terms are alternatively positive and negative. So it goes positive term, negative term, positive term, negative term. So here, what's happening to the partial sums is the partial sums are stepping up and down, okay? Because half the time you're adding a term on, the other half of the time you're subtracting a term off. So your partial term is oscillating up and down, your partial sum. So the only way that's going to converge is if the AM, which is the absolute value of the series term, if those are decreasing and converging to 0. If that step size is decreasing and converging to 0, then your oscillating partial sum will be settling down and zeroing in on some limiting value. Again, the series test, it doesn't tell you what the limiting value is. It just gives you a conclusion about the nature of the behavior, whether it's convergent or divergent. Another useful test is the ratio test. This one is, so here we examine the limit of the ratio of terms of the series. So you're kind of like comparing the series to itself in a way. Now this is most applicable to series where when you form this ratio, am plus 1 divided by am, where that's going to simplify a bit. And that's typically the case where the definition of am involves powers of am or factorials of m, so on. Any kind of term, any kind of operation on m such that when you form a quotient of it, it'll simplify down nicely. It needs to simplify so that you can determine what the limit of that sequence of ratios is. And if you determine that the limit of that sequence of ratios is some limit L, then depending on the value of L, you can draw a conclusion. If L is between 0 and 1, so if it's positive but strictly less than 1, then you know your original series is convergent. If L is strictly bigger than 1, then you know your series is divergent. The trouble is, if the borderline case, if the value of L comes out at exactly 1, you're stumped. The ratio test doesn't tell you anything. It's because your series is kind of hovering on the border between convergent behavior and divergent behavior. So you need to examine it a lot more closely to determine which side of the borderline it is. And this is justified. The justification for the ratio test is because what you're doing is you're establishing that the terms of your series are eventually acting like a similar geometric series. So if the ratio am plus 1 divided by am, if that's close to L, then that means that your am plus 1 will be close to approximately L times am. Now, if this was equals, if each term in your sequence was exactly L times the previous term, that would be a geometric series. Yeah, but it's not exactly, because the ratio is only approaching L, it's converging to L. So eventually this will be a good approximation. So eventually the terms of your series are acting pretty much approximately like the terms of a geometric series. And the geometric series we know will be convergent if that common ratio L is strictly less than 1, and divergent if it's bigger than 1. But equal to 1 is the borderline, and because this is only an approximation, you're not sure which side of the borderline your series is. So you have to examine it a lot more closely to determine what the convergent behavior is. I think this is the final one. Yeah, the root test. So the root test again, this doesn't apply that much. So this is where we take the nth root of the nth term of your series, which for typical expressions in M, taking the nth root is probably quite awkward, and it's probably quite hard to determine what the nth root of just a random expression in M is going to look like. But in some certain situations, really where the last operation applied in constructing AM, if the last operation applied was raising to the power n, or raising to some power closely related to m, then taking the nth root of that will simplify. Because taking the nth root of this will nullify the effect of raising to the nth power. And so the nth root of am will just be the term inside the bracket, which is a lot simpler than am. So in such cases, you might be able to determine what the limit of the nth root of the nth term is. That comes out as some value L. And again, you draw conclusions about it the same way for the ratio test. If L is strictly less than 1, your original series is convergent. If it's strictly bigger than 1, it's divergent. And again, the L equals 1 case is a borderline case as well. So you can't conclude, you can't draw any conclusions if the limit comes out as exactly equal to 1. Final slide there is just a reference and a reminder, you know, on top of everything else, you got all the exercises in the notes. You've got the 2 separate series and sequences, tutorial sheets that are up on Moodle. Their solutions are up on Moodle. Solutions to all the exercises and the notes are up on Moodle. For even more ammunition to work with, the Sham's Outline of Calculus book is very good. This is the link to its entry in the library system. It's accessible as an online ebook. So if you look at these slides on Moodle, click on that link. This link is clickable here. Click on that. It'll take you to the entry for the book in the MMU library. And from there, click on the button, access the ebook. You'll eventually get to access it. And if you look at the relevant chapters there, if you look in the relevant chapters, you'll find lots of practice exercises on sequences, convergence of sequences and series. Okay, so let's take a little 10-minute break now. So we'll start again. It's 9:53 now. We'll start again a couple of minutes after 10. We'll look at the mock tests in detail, and I'll take any questions that you might have then as well. Okay? Hi.